Hello and welcome to another math chat by Faith. This is another one that you are watching. You don't just watch one, you watch multiple. Okay. IEB May 2024 paper 1. We're looking at question 1F. Consider the equation x plus k squared is equal to 2k plus 1. Solve for x in terms of k. So thankfully, in our equation, we only have one occurrence of x, the way that it's, currently set up. So the job of isolating the x is actually not too messy, right? Or messy, by messy, I mean, fewer steps. So we need to basically remove all the onion layers until we just have the x. First thing that is entrapping this x is this square, so we need to get rid of the square. Once we get rid of the square, the next thing we need to get rid of is this friend over here, this k. Then we will be able to have the x by itself. So that is the mission that we are going on. Let's do it. So I'm just going to write out the equation again. Okay, so the first thing we said we need to get rid of is the square. And we're going to do that by taking the square root on both sides. And remember that it could be a positive or a negative root, right? So this will then be x plus k is equal to plus or minus square root of 2k plus 1. Okay, and then from there we can minus k on both sides, right? And we'll be left with x is equal to, and just looks nicer to put that minus k in the beginning, right? Plus or minus the square root of 2k plus 1. And like I always say, nice thing about an algebra paper is that you can kind of quickly test some of these things, right? So you can choose any value for k, well, any real value for k, right? So let's test with k is equal to 5. Let's be adventurous. So then our left hand side would be, so this is now looking at the original equation, right? So the left hand side would be x plus 5 squared. And for argument's sake, I'm going to just expand this, right? So 5x plus 5x is 10x, and 5 times 5 is 25. And then the right hand side would be 2k plus 1, so that is 2k plus 1, which is 11. So now the task would be, firstly, to add a new page. Okay, so the task would be, given this equation, right, which is what the equation becomes when k is equal to 5, we want to find the solutions. And in fact, you know what, I could actually even try to be nice to myself and choose better numbers, because this k is equal to 5 is going to give me nightmares. So basically I want to find a number such that 2k plus 1 will end up being a perfect square. So let's make 2k plus 1 equal to 9. So that means my k needs to be 4, because then 2 times 4 plus 1 is 9, and then hypothetically this should work out nicely, because then it will be square root of 9, so sometimes we got to be smart about these things, not give ourselves unnecessary chest pains. So whoa, I'm going to choose some random number. Okay, so I'm actually going to use k is equal to 4. So then the left hand side of my equation, which is x plus k squared, will be x plus 4 squared. And if I expand that, that actually ends up being 4x plus 4x, and the last term ends up being 16. And then on my right hand side, which is 2k plus 1, that will be 2 times 4 plus 1, which is 9. So then this is actually the equation we want to solve. X squared plus 8x plus 16 is equal to 9. Right, so now what we want to see is, okay, if we solve this equation, do we end up with these solutions, right? So we should end up with x is equal to minus k plus or minus 2k plus 1 as our solutions, right? And what are those actually? So that is x is equal to minus 4 plus or minus the square root of 9, which is minus 4 plus or minus 3. So either x is minus 4 plus 3 or x is minus 4 minus 3. So these are the two solutions we should end up with. Right, so let's see what we get. Where was I? Why do I feel like I started in a different... Oh, I'm testing. Anyway, so we are back to solving this guy and seeing what solutions we get. So to do that, I can get everything to one side. So 16 minus 9 is 7. And so we end up with x plus 7 times x plus 1. And indeed, our solutions are x is equal to minus 7 or x is equal to minus 1. So we can be fairly confident that, you know, this expression does in fact represent the solutions for this equation, no matter what value of k I choose. And you could go ahead and do the example with an ugly number like 5. No hate 5. And see that you do in fact get the solutions if you were to solve this equation, you know, the normal way that you know how to solve it, and versus, you know, using this expression that gives us kind of the general solution for this equation. Anyway, so next question says, hence or otherwise, no pressure, write down two positive values of k for which the roots are rational and real. So hence or otherwise, write down two positive values of k for which the roots are rational and real. Okay, so I mean, one of the k values would be 4, right? Because here are two rational and real roots. Oh, but they're not positive. Oops, sorry. Okay, so we want x to be rational and real and wait, what must be positive? I'm so confused. Write down two positive values of k. Oh, sorry. So k is equal to 4 is one possible value, right? Because it's positive and the roots are rational and real. These are the roots, they are rational and real. So, sorry, I was getting myself confused because English, so many big words. Right, so how could we go about this more generally? I mean, of course, the otherwise, it wouldn't even be an otherwise, right? Well, the otherwise would be to just trial and error, try as many numbers until you find two positive values that give you rational and real roots. Obviously, that would be a lot of work, so we do want to use this somehow. So the question is, how can I end up with rational and real roots here? I feel like I've said so many words, and I don't know if I'm really saying anything. Anyway, so k must be positive, so that's requirement number 1. Requirement number 2, minus k plus, okay, there's no need to write out that whole expression. X must be rational and real. Okay, so the biggest thing then is, the biggest thing governing whether it is rational and real is this. Because think about it, the k, right? If we kind of make k an integer by default, right? Like, let's not complicate our lives and think of k being maybe 2.5 or no. Let's just peg k as being an integer. Then this bit of the expression will be rational and real. This part of the expression will be dicey, depending on what k exactly we use. So if we can get 2k plus 1, to be A, real, i.e. it must be greater than or equal to 0, okay? Because if it was smaller than 0, then we'd end up with a non-real situation. And then secondly, we need it to be a perfect square, right? So that you know, the square root doesn't make it funky, doesn't make it irrational. So then we can pretty much do what we did, so what I did for the testing in the previous question, right? We can say, okay, so pretty much true k plus 1 must be greater than or equal to 0 means that true k must be greater than or equal to minus 1, which means k must be greater than or equal to minus a half. Okay, so this is our pool. On the number line, we're looking at k's greater than minus a half, sharp. So that satisfies this requirement. Now we just need to pick a number such that true k plus 1 will be a perfect square. And that can be anything, right? Because so the smallest value of 2k plus 1, if we're looking from minus a half onwards, is going to be let's explain what we're saying here. 2k plus 1 will be 2 times minus a half plus 1, which will be minus 1 plus 1, which is 0, which is actually oh, but this is not a positive value for k, so minus a half doesn't count. Right, so why did I do that? Yeah, no, in post editing there must be crickets for that. I don't think I needed to do that. Okay, the point is, if we look at anything above minus k is equal to minus a half, we are good. Why did I do that? Oh, I guess, okay, I guess maybe, no, it wasn't necessary to do that anyway. So any square is fair game. I think that's what I was trying to get at, but yeah, just by virtue of us choosing a k such that 2k plus 1 will be greater than or equal to 0, that establishes that any square, I can choose any square to make 2k plus 1 equal 2. There isn't a restriction on that. So anyway, I can choose k such that 2k plus 1 is equal to 1, right? So then 2k is equal to 1 minus 1, so k is equal to 0, right? So if k is equal to 0, let's see what happens here. You then end up with x plus 0 squared, so x squared, I'm just going to write this down. You end up with x squared is equal to 2 times 0, so nothing, plus 1. And so you end up with x is equal to plus or minus 1, right? So you end up with 2 rational roots. So that is k is equal to what? 0. Okay, but 0 is not a positive number. Yeah, so k needs to be greater than 0. So sorry, 0, we don't want you here. So let's choose another number. Let's choose 2k plus 1 such that it is equal to the next square, 4. So then 2k is equal to 4 minus 1, and so k is equal to 3 over 2. Oh, yeah, that one's going to be a messy one to test. But let's see. So that will be x plus 3 over 2. Yeah, I don't want to test this. Is equal to 2 times 3 over 2, which is 3 plus 1, which is 4. Okay, not too messy. So you could then multiply it out and, you know, put it into the quadratic formula, whatever. But it's easy to see that, if you take the square root on both sides, so you're going to end up with plus or minus 2 here, and then you minus the 3 over 2, so then the roots are going to be rational, they're going to be real. So that does satisfy it. Our k is 3 over 2, which is greater than 0, so that requirement is satisfied. So this is an example of a value that we could choose. And then you could choose k, anything from there really, such that 2k plus 1 is equal to 100, right? Any square, other than the first one we tried. Okay, so I keep choosing weird ones. Okay, maybe let me not choose even numbered squares. Let's choose 49. So then you'll have 2k must be 48. So then k would be equal to 48 over 2, which is 24. And that would be another value that would work, right? So let's see how the equation would look. It would be x plus 24 squared is equal to 2 times 24, which is 48, plus 1, which is 49. So you'd end up with x plus 24 squared is equal to 49. And again, you take the square root on both sides. Square root of 49 is 7, and then you would you'd minus the 24, so again you would end up with real rational roots, and your k would be a number that's greater than 0, so then happy days. So really the choices are limitless, because you could choose any square as long as 2k plus 1, well, as long as the k is greater than 0, Anyway, definitely a very chaotic explanation, but I hope that made sense. And yeah, I think that's a good place to land the plane, and I'll catch you guys another time.